We present PAPRLE, a modular ecosystem for robotic limbs. With PAPRLE, users can flexibly arrange diverse leader-follower setups and control of various configurations through a unified teleoperation framework. By supporting a wide range of follower configurations and leader devices, PAPRLE provides a flexible and scalable solution for large-scale data collection. In our prior work, we introduced PAPRLE, the plug-and-play robotic arm system. PAPRLE enables flexible hardware configurations by allowing robotic arms to be mounted in various places, enabling varied use cases. Building on this plug-and-play concept, PAPRLE extends this idea to teleoperation domain. We developed pluggable puppeteer devices that can be freely mounted to the system, as many as needed. This modular design allows users to teleoperate diverse multi-limb configurations of PAPRLE arms with ease. As robot learning increasingly depends on large-scale datasets, teleoperation has become a critical tool for data collection. While many existing works have made significant progress in teleoperation, they are often tightly coupled to specific hardware setups. This makes it challenging to support broader diversity both on the leader and follower side. In contrast, PAPRLE is not limited to specific leader devices or follower robots. Users can plug in the leader device of their choice and pair it with the desired follower robot. Here are examples of diverse configurations using a pair of PAPRLE arms. They can be mounted on a table for tabletop tasks, on top of a counter or wall for extended workspace, or on a mobile platform for mobile manipulation tasks. Leader configurations for these setups can be easily arranged using our pluggable puppeteer devices, which can also be mounted in various positions to match the follower configuration. Beyond the pluggable puppeteer devices, a wide range of leader devices can be used to control the same follower robot. These include puppeteer devices with different structures from PAPRLE, as well as gaming controllers, VR interfaces, or even pre-recorded data from other sources, allowing users to choose the leader interface that best fits their preference and target task. This is the overview of the PAPRLE teleoperation system. The system is modularized with 4 modules, allowing the users to plug and play leader and follower components as needed. PAPRLE supports both task space and joint space control, enabling teleoperation between heterogeneous setups. For example, a puppeteer with a UR5-like structure can control a PAPRLE arm with a very different kinematic structure. The signals from leader are translated into joint position commands and forwarded to the follower robot. PAPRLE is compatible with a wide range of environments. For hardware, both ROS1 and ROS2 are supported, and for simulation, MuJoCo, IsaacGym, and Gazebo are supported. For puppeteer devices, PAPRLE provides force feedback to the leader, enhancing the user awareness even when the leader and the follower has different joint configurations. PAPRLE implements 2 types of feedback: intrinsic feedback and extrinsic feedback. Intrinsic feedback is based on the leader model itself. It works as a bias term to maintain the puppeteer in a stable configuration, helping the operator to move more freely. Without intrinsic feedback, a multi-joint puppeteer device can easily collapse or collide with the environment. Such situations are highly undesirable during teleoperation, as they can disrupt control and potentially damage the hardware. Extrinsic feedback is generated from the discrepancy between the leader's command and the follower's actual state. It provides the operator with physical cues that reflect collisions, contact forces, or kinematic constraints. This is the example of force feedback when they share same kinematics. Here, the operator pressed the gripper too fast. The force feedback is generated in opposite directions. Then, the operator moved too fast, so the force feedback is generated to push each joint of puppeteer towards the follower pose. This is the example of force feedback when the leader puppeteer and the follower have different joint kinematics. In here, the operator moved too fast. Force feedback is generated to push leader's end effector pose towards the follower end effector pose. Using Jacobian matrix, the force feedback for each joint can be calculated. For the gripper, extrinsic feedback is generated based on the joint position differences. Here is an example of gripper-level feedback. As the follower robot grasps an object, the discrepancy between the commanded gripper pose and the actual follower gripper pose naturally happens. The operator can feel the resistances. If they push harder, the feedback force increases, guiding them towards safer grasps. Now we show demonstrations of PAPRLE across diverse follower configurations. Here, these are the examples of controlling the same follower robot using different leader devices, demonstrating the versatility of the PAPRLE interface. PAPRLE also supports streaming the pre-collected data to follower robot. In this video, the PAPRLE arms reproduce the motion collected from UMI, Universal Manipulation Interfaces. Using PAPRLE, we can efficiently collect demonstration data for training robot learning policies across varied tasks and platforms. These are example videos demonstrating the dataset collection process. This slide shows an example episode of collected dataset. We trained a manipulation policy using data collected with PAPRLE. The results show that PAPRLE provides a reliable foundation for data collection in real-world settings.